Welcome back to Engineering Out Loud, listeners, for our second deep dive from MECHESOL's MESP Engineering Development Program. Are you ready to explore the world of machines that build everything around us?
Absolutely.
If you're interested in an exciting career designing, building, and optimizing these manufacturing systems, head over to mechesolco.com/CPD. Apply to our MESP Engineering Development Program.
It's going to be a fascinating journey today. We'll unpack how these machines work, why they're so important, and how they're evolving.
Okay, let's start with the rock stars of the factory floor. Cutting machines. CNC, laser, and water jet cutters. I'm already picturing lasers slicing intricate jewelry, and water jets powerful enough to cut through steel. But what makes these cutting machines so special?
It's all about precision and control. Imagine programming a computer to guide a tool that can carve metal with micron-level accuracy. That's what CNC machines do.
Wow, it's like a robot sculptor, working tirelessly on super detailed projects. So what makes CNC machining so sought after in manufacturing?
Well, it allows for incredible design freedom. Think complex geometries, tight tolerances, and repeatable cuts, all executed with incredible speed and consistency. CNC machines can produce thousands of identical parts, each one perfect, which is why they're so crucial for mass production.
That's mind-blowing. And then we have laser cutters. I read that they're so precise because the laser doesn't actually touch the material.
That's right. A high-powered, focused laser beam vaporizes the material, essentially making a super clean cut with minimal heat. This is critical for working with delicate materials or parts that can't be distorted by heat, like those found in electronics or aerospace applications.
Okay, that makes sense. So no physical contact means less wear and tear, right? What does that mean for efficiency and cost savings?
Exactly. Reduced tool wear translates to less downtime for maintenance and longer tool life, which directly impacts production costs. Laser cutting is fast and precise, minimizing material waste.
That's incredible. And what about water jets? How can a jet of water be powerful enough to cut through metal, but also delicate enough to slice a tomato?
It's all about pressure. Water jet cutting uses extremely high-pressure water mixed with abrasives to erode the material away. It's a cold cutting process, meaning no heat distortion. This allows for intricate cuts on a wide variety of materials, from delicate fabrics to thick steel plates.
So you're saying I could use a water jet to cut out a pattern for a dress, then turn around and slice through a steel beam.
Exactly. And the beauty of water jet cutting is that it's incredibly versatile. You can cut complex shapes without needing specialized tooling, and there's minimal material loss. This is a big deal when working with expensive materials.
Okay, I'm starting to understand why these cutting machines are so vital to modern manufacturing. They offer a unique blend of precision, speed, and versatility, making them essential for countless industries. Speaking of unique blends, what's next on our manufacturing machine tour?
Let's move on to molding, where we'll explore how machines are used to shape molten plastic into countless everyday objects. If you want to shape your own career in engineering, visit mechesolco.com/CPD and register for the MESP Engineering Development Program.
All right, let's break down these molding methods. I know we've got injection molding, blow molding, and compression molding, but why are there so many different ways to mold things?
Because each method is designed to create specific types of parts. Injection molding is perfect for high-volume production of intricate parts. Molten plastic is injected into a mold under high pressure, and once it cools, you have your part. Everything from bottle caps to complex gear assemblies.
So it's all about speed and efficiency.
Exactly. And the beauty of injection molding is that you can create parts with extremely fine details and complex geometries, which is why it's so popular for consumer electronics, automotive components, and medical devices.
Okay, injection molding is for those intricate mass-produced parts. What about blow molding? I know it's used for things like bottles. How does that work?
Blow molding is like inflating a balloon inside a mold. You start with a heated tube of plastic called a parison, place it in a mold, and then blow air into it until it conforms to the mold's shape.
That's a great visual. It's like creating a hollow part from the inside out. What are some of the key benefits of this method?
It's an incredibly efficient way to create hollow parts. Think about water bottles, shampoo bottles, fuel tanks, or even some medical implants. Blow molding allows you to create these complex shapes with thin walls using less material than other methods.
So it's cost-effective and more environmentally friendly.
Absolutely. Blow molding is a prime example of how engineers are constantly innovating to reduce waste and improve efficiency in manufacturing.
That's awesome. So we've got injection molding for the small, intricate parts, and blow molding for the hollow, lightweight parts. What about compression molding? What kinds of products utilize this method?
Compression molding is more about strength and durability. It uses heat and pressure to squeeze a preformed material, often a thermosetting plastic, into a mold. Think about electrical components that need to withstand high temperatures, automotive parts that need to be impact resistant, or even cookware.
Wait, thermosetting plastic? What's that?
These are plastics that undergo a chemical change when heated, becoming permanently hardened. They're known for their strength, heat resistance, and dimensional stability, making them perfect for demanding applications.
So compression molding is the go-to for parts that need to be tough and resilient. It's fascinating how each of these molding methods has its own strengths and weaknesses, and how engineers have to carefully consider which one is best for a specific application.
Exactly. It's all about understanding the materials, the desired outcome, and the most efficient way to achieve it.
And that wraps up our deep dive into molding machines. We've learned about injection molding for complex parts, blow molding for hollow parts, and compression molding for strength and durability. You've got my head spinning thinking about all the products around me that are made with these methods.
There are countless examples, but before we move on, I want to remind you that if you're interested in exploring the world of manufacturing further, visit mechesolco.com/CPD.
You got it. Now let's talk about forming machines. These are the heavy lifters that bend and shape metal with incredible force.
Forming machines are all about transforming flat sheets of metal into complex, three-dimensional shapes.
It's like metal origami. I'm picturing massive machines bending and shaping metal with incredible force, but how do they actually achieve that?
There are various methods, but some of the most common ones include press brakes, rolling machines, and forging presses. Each utilizes different principles to manipulate the metal.
Let's start with press brakes. I imagine they're used for creating those sharp bends and angles you see in sheet metal parts. Am I on the right track?
Exactly. Think about the panels on a car, the casing for an electrical enclosure, or even the brackets that hold up shelves. A press brake uses a punch and a die to force the metal into a specific shape.
So it's like a giant metal folding machine. What are some of the advantages of using a press brake over other forming methods?
Press brakes are incredibly precise and can create complex bends and shapes with repeatable accuracy. They're also relatively fast and can handle a wide range of material thicknesses, making them versatile for various applications.
Okay, press brakes are for bending and folding. What about rolling machines? I know they're used to create curved surfaces, but how do they work?
Rolling machines use a series of rollers to gradually bend and shape the metal. Imagine feeding a flat sheet of metal through two rollers that are slightly offset from each other. As the sheet passes through, it starts to curve.
It's like using a rolling pin to flatten dough. But instead of flattening, it's curving the metal.
That's a great analogy. By adjusting the distance between the rollers and the number of passes, you can achieve different curves and shapes. Rolling is often used to create cylindrical shapes like pipes and tanks, but it can also create cones and other complex curves.
That's incredible. So you can create everything from a simple curve to a complex three-dimensional shape using rolling machines. What about forging presses? I know they're known for creating incredibly strong parts. How do they work?
Forging uses compressive force to shape metal, often at elevated temperatures. Think about a blacksmith hammering a piece of hot metal to shape it. A forging press works on a similar principle, but on a much larger scale.
So it's like squeezing the metal into the desired form. But why does forging create such strong parts?
Forging actually changes the internal structure of the metal. By hammering or pressing the metal, you're aligning the grain structure, making it more resistant to stress and fatigue.
So it's not just about shaping the metal, it's about improving its internal properties. What are some of the advantages of using forged parts over parts made with other methods?
Forged parts are known for their strength, durability, and reliability. They're often used in high-stress applications like engine crankshafts, gears, turbine blades, and even some aerospace components.
Okay, I'm starting to understand why forging is so critical for those demanding applications. So we've got press brakes for bending, rolling machines for curving, and forging presses for shaping and strengthening metal. These forming machines are truly shaping the world around us.
Absolutely. And if you're inspired by the ingenuity of these machines, and you want to be a part of shaping the future of manufacturing, then I encourage you to visit mechesolco.com/CPD and apply today.
Now let's shift gears and talk about joining machines. These are the machines that bring different parts together, creating the final products we see and use every day.
From the smallest electronic components to massive bridges, joining machines are essential for creating the structures and devices we rely on.
All right, let's dive into the world of joining. I know there are several methods, but we'll focus on the big players.
Welding.
Welding, soldering and brazing, and riveting. What are the key differences between these methods?
It all comes down to how the bond is created. Welding uses heat to melt the base materials together, creating a strong, permanent joint. Soldering and brazing use a filler metal that melts at a lower temperature than the base materials, flowing between them to form a bond. Riveting, on the other hand, uses a mechanical fastener to join the materials.
Okay, so welding is about melting. Soldering and brazing are about flowing filler metal, and riveting is about mechanical interlocking. That's a great way to remember the basic principles. Let's start with welding. It seems to be the most common joining method. Why is that?
Welding is incredibly versatile and creates extremely strong joints. It's used across countless industries, from construction and shipbuilding to automotive and aerospace. There are many different welding techniques, but they all rely on using heat to melt the base metals and create a fusion bond.
What are some of the advantages of using welding over other joining methods?
Welding creates incredibly strong bonds that can be as strong as or even stronger than the base materials. This makes it ideal for structural applications where strength is critical. Welding is also relatively fast and efficient, especially when you consider the strength of the bond it creates.
So strength, versatility, and efficiency are the key benefits of welding. But I imagine there's some drawbacks too, right?
Of course, welding requires skilled operators and specialized equipment, which can be expensive. It also generates heat and fumes that can be hazardous if proper safety precautions aren't taken. And because the base metals are melted, there's always a risk of distortion or warping, especially when working with thin materials.
Okay, so welding is powerful, but needs to be handled with care. What about soldering and brazing? I know they're often used for smaller components or when working with delicate materials. What are some of the key differences between these two methods?
The main difference lies in the temperature. Soldering uses lower temperatures, typically below 450 degrees Celsius, while brazing uses higher temperatures above 450 degrees Celsius. This difference in temperature affects the strength and properties of the joint.
So brazing creates a stronger bond than soldering.
Generally, yes. Brazing is often used for joining metals that will be subjected to higher stresses or temperatures, while soldering is typically used for electronics, plumbing, and jewelry making.
It seems like soldering is better suited for delicate work, while brazing is for more heavy-duty applications. What about riveting? It's one of the oldest joining methods, but it's still widely used today. Why is that?
Riveting is a simple, reliable, and cost-effective method that creates strong mechanical joints. Unlike welding or soldering, it doesn't require heat, which makes it ideal for joining dissimilar materials or materials that are sensitive to heat.
So no heat means less risk of distortion or damage to the materials. What are some of the key advantages of using riveting?
Rivets can be used to join a wide variety of materials, including metals, plastics, and composites. They're also relatively inexpensive and easy to install, requiring only basic tools. And because rivets create a mechanical interlocking, they're resistant to vibration and fatigue, making them perfect for applications where those factors are a concern.
Okay, so rivets are simple, reliable, and perfect for joining dissimilar materials. But are there any downsides to using rivets?
One drawback is that riveted joints are not as strong as welded joints, so they're not typically used for structural applications where maximum strength is required. Rivets also create holes in the materials being joined, which can weaken the overall structure if not carefully considered.
That makes sense. So it seems like each joining method has its own strengths and weaknesses, and engineers have to carefully consider which one is best for a particular application.
Exactly. Choosing the right joining method is crucial for ensuring the integrity, functionality, and longevity of the final product.
And that wraps up our discussion of joining machines. We've covered welding for strength and versatility, soldering and brazing for delicate and high-temperature applications, and riveting for simple, reliable, and cost-effective mechanical joints.
It's amazing to see how these joining methods, along with the cutting, molding, and forming techniques we discussed earlier, all come together to create the products we use every day.
It's like a symphony of engineering.
Wow!
We've covered a lot of ground in this deep dive, from cutting and molding to forming and joining. It's amazing to see how all these different machines work together to transform raw materials into the products we use every single day.
It really highlights the ingenuity and creativity of engineers who design, build, and operate these incredible machines.
I'm especially fascinated by how each machine plays a specific role in the manufacturing process. They're like specialized tools in a giant toolbox, each with its own strengths and limitations.
That's a great analogy. And just like a skilled craftsman chooses the right tool for the job, engineers carefully consider which manufacturing process is best suited for a particular product and its intended use.
So it's not just about having the coolest machines, it's about understanding the materials, the design requirements, and the most efficient way to achieve the desired outcome.
Exactly. It's a delicate balance of science, engineering, and artistry.
And as technology continues to evolve, I can only imagine how these machines will become even more sophisticated and efficient. What do you think the future holds for manufacturing?
The possibilities are truly exciting. We're already seeing advancements in automation, robotics, and artificial intelligence that are transforming the manufacturing landscape. Imagine machines that can 3D print complex parts with intricate details, robots that can assemble products with superhuman precision, and AI systems that can optimize manufacturing processes in real time.
It sounds like the factory of the future will be a truly remarkable place.
Absolutely. And for those of you who are intrigued by the world of manufacturing and want to be a part of this exciting future, I encourage you to visit mechesolco.com/CPD.
It's a fantastic opportunity to explore the MESP Engineering Development Program and see how you can contribute to the next generation of manufacturing innovation.
Remember, the products that shape our world don't just magically appear. They're the result of careful planning, innovative engineering, and the skillful use of these incredible machines.
So the next time you pick up your smartphone, drive your car, or even just flip on a light switch, take a moment to appreciate the amazing journey that product has taken from raw materials to finished good. And think about the incredible machines and the brilliant minds that made it all possible.
Thanks for joining us on this deep dive into the world of manufacturing. We hope you've gained a newfound appreciation for the machines that shape our world.
And if you're interested in learning more about how you can be a part of this exciting field, don't forget to visit mechesolco.com/CPD.
Until next time, keep exploring, keep learning, and keep engineering out loud.